Our last topic of the unit, 4 school days before our unit test coming up next Monday, is satellites. Let's define a satellite. A satellite to us is anything that revolves around something else. Technically, as I walk around this room, around the outer edge of this room, I'm a satellite of all of you. I'm revolving around, well, not all of you, but most of you as I walk around this. I'm a satellite. I'm revolving around something else. Now, when we talk about satellites, though, we're not talking about guys walking around a classroom. We're talking about what we think of as satellites, right? That is things that orbit around the Earth, or things that orbit around conceivably some other planet or a moon or the sun. Something in space that orbits around something else. There are two types of satellites. You may not think of the moon as a satellite, but it is. The moon orbits around the Earth. You may not think of the Earth as a satellite, but it is. The Earth orbits around the sun. Those are natural satellites. Those are satellites that we didn't put there. They're just there. Versus artificial satellites, which are satellites that we did put there. ISS, by the way, stands for what? The International Space Station that orbits around the Earth. Do you know the International Space Station is only about 400 kilometers up? It's only about 400 kilometers up. But that's space, at least it's the edge of space. It orbits around the Earth at an altitude of about 400 kilometers, give or take a little bit, and we put it there. That's an artificial satellite. That's typically what we think of when we talk about satellites, right? It's things that we put there. Communication satellites, spy satellites, artificial satellites. But things like the Earth revolving around the sun and the moon revolving around the Earth, they're satellites as well. They're just natural satellites, that's all. They're there on their own. Just out of curiosity, how many of you guys have ever seen the International Space Station? How many of you guys have physically seen the space station? It's only 400 kilometers up. If you look up in the sky at nighttime, at the right time, you can see very clearly the space station going overhead. You can't see details. Okay, you can't see what color it's painted, or you can't see an astronaut looking out the window waving. But you can see this bright flash of light going across the sky, and it's unmistakable. You will not mix it up for an airplane. If you think, is it an airplane or is it the space station, then it's an airplane. Is it a star or is it the space station, then it's a star. Okay, when you see the space station, you'll know that it's the space station orbiting overhead. It's the brightest light in the sky, and it's moving fairly quickly across the sky, and it's way too high up to be an airplane. There is a website, that's actually the NASA website, where we can actually check any single town or city in the world to see when we should look up in order to see it. I've looked up and seen it sometimes just by accident, just because, whatever, you're outside, it's dark, it's not cloudy, and you just happen to notice this thing go across. Hey, it's a space station. But I've also looked at specific times as well when I've looked on this website. We're going to real quickly check this website, and we're going to see when the next passing of the space station is. We're going to see, and we'll have a look. Let's see, what's today? The 9th, right? Okay. There's one tonight, actually. Not a very good one, because you can see that it lasts for less than a minute, and it's only 12 degrees above the horizon. 12 degrees above the horizon, you'd have to be out in a pretty flat field with nothing around in order to see that. Because basically, it's looking out, okay, it's kind of like this, right? Very, very low. Okay? You'd have some difficulty probably seeing that one. Thursday, it lasts 4 minutes. That's a good one, but it's only 17 degrees above the horizon. We don't see a real good one until probably about Friday, I guess, yeah. Friday, 45 degrees above the horizon. That's pretty good, actually. Okay, look up at 45 degrees, you should see it. It lasts for 2 minutes. And 6:34 p.m., that's perfect, actually. It's dark. Okay, as long as it's not cloudy outside, then you should have no issue seeing that one whatsoever. Where should you look? Well, it's 18 degrees above southwest, 45 degrees above southeast, it disappears. So that's southwest, that's southeast. You're going to look up, okay? You're going to look up in the southeast, southwest like this, and then it's going to go across the sky like this, and then 2 minutes later it's going to be over there, and it's going to disappear. It will be a bright light. It will be high up in the sky. It will be unmistakable. Okay? You're looking at something in space where people are on board, maybe even looking out at you. Okay? So Friday night, you guys are going to have a look up in the sky, right? 6:34 p.m., you're going to see that space station in the southwest disappearing in the southeast. Now, satellites are going to travel, we said, more or less in a circular orbit. Elliptical, right? Sometimes it's elliptical orbit, okay? But it's close to a circle, so close to a circle, in fact, that we can consider it to be a circle. And the satellites that we're going to be talking about, space station going around the Earth going around the sun, the moon going around the Earth, they're going to be held in place by gravity. So we got a centripetal force that's keeping in the circle, but really the centripetal force is just gravity, kind of renamed. When a car goes around a turn, the centripetal force is caused by friction, and we can set those two forces equal to each other. When the electron goes around the nucleus of the atom, the centripetal force is caused by an electric force. We can set those two equal to each other. When the Earth goes around the sun, or when the space station goes around the Earth, the centripetal force is caused by gravity. We can set those two equal to each other. So, whenever we're going to analyze a satellite, this is what we're going to do. FC equal to FG. MV squared over R equals, you want to say M times G? I so want to say M times G because that's a simpler equation, but we don't know what little g is. So we're going to use the general form of the force of gravity equation, G M1 M2 over R squared. Now, if you don't like math, you might not like this next step. I'm going to get rid of an R because on the left side we got one R, on the right side we got two R's. Hold on, let's cancel out one of the R's. I'm also going to get rid of the mass, one of the masses. What mass am I getting rid of? The producer or the experiencer? In other words, the Earth, we're talking about the Earth and a satellite. Which one are we canceling out? It does matter. Which one are we canceling out? This would be, let's cancel that in a second here. This would be the mass of the producer, the mass of the experiencer. Which mass is this one over here? MV squared over R, which mass do we use? The mass of the satellite going around the Earth or the mass of the Earth that's causing the field? Lewis? Sorry? The satellite or the experiencer, right? So we're going to cancel out the mass of the experiencer, which leaves us with this equation. V squared is equal to G times the mass of the producer over R. Not R squared, just over R. Now, this is the equation that you're going to end up using quite a bit to solve satellite problems. It does not appear on your data sheet. Okay? FC is equal to MV squared over R does. FG is equal to G M1 M2 over R squared does. You got to put them together and then derive this one. And then rearrange this one to solve for whatever you're looking for, V or R or whatever the case may be. Tomorrow we'll do a couple problems with this, and then we'll basically be done our unit. Homework tonight, remember guys? It's those two sets of practice problems. One of them many of you have done already. The other one, make sure you get that done, please. Okay, that's it for today.